Hello again. It's time for section 7.4. Okay, so this is section 7.4 called Nucleophilic Strength and Solution Effects with SN2 Reactions. And we touched on it a little bit in 7.3, but it's important to note that some nucleophiles are stronger than others. And so the question is, what makes a strong nucleophile? Well, in general, there are a couple things that you should look out for that'll help you to know if a nucleophile is strong or not, or it should be strong. First, look for negative charge or high electron density on the molecule, like in these types of negatively charged potential nucleophiles, like alkoxides, where R can be any alkyl group, such as methoxide or ethoxide. Look out for negatively charged anions, like this cyanide anion, or negatively charged halide ions like chloride, bromide, and iodide. Each of these can be strong nucleophiles. The second thing that makes a strong nucleophile is polarizability. If a molecule is very polarizable, you can have partial positives and partial negatives that build up in the atom itself or the ion itself to make a very strong nucleophile. This really happens a lot in iodide and sulfur, but also in bromide too. So you can have thiolates, which are these that are alkyl thiol anions, such as methyl thiolate or ethyl thiolate, in addition to iodide and bromide. And they're very polarizable mainly because of their size. They have a lot of electron density very far away from the nucleus, so it's kind of easy for the electron density to slosh around more or less and have one side with a little higher electron density than the other. So next, we're going to talk about some solvent effects in SN2 reactions, or in SN2 reactions, because SN2 reactions have to be run in some solvent. You don't have just some alkyl halide and nucleophile just floating around in the air. They have to be dissolved in something, and so that something can play a very big part in determining the reaction rate of the reaction. So what you should know is that SN2 reactions require a polar solvent, and there are two types of polar solvents that you will run into. One is a polar solvent that does not have an acidic proton that can participate in hydrogen bonding, and these are called aprotic polar solvents. There are also protic polar solvents, which all have acidic protons that can also participate in hydrogen bonding. And typical protic polar solvents are water, methanol, and acetic acid, among others like ethanol. And aprotic polar solvents are those like acetone, DMF, and DMSO. Those are the ones that we'll probably run into the most in this course. And if we specifically want to talk about the effect of solvent on reaction rate, we can look at these a lot in a similar manner to how we looked at alpha-beta position effects on reactions. So if we take iodomethane and we submit it to some nucleophile, we will then displace the iodide anion and end up with a methyl nucleophile bond that's formed. Okay, so we have to say this is going to be, these reactions are run at 25 degrees Celsius because temperature can play a big role, as we remember from our thermodynamics lecture. So if we just look at the nucleophile and how that changes with the solvent, or how the reaction rate changes with this type of solvent, we might get a good idea of what types of solvent effects have on SN2 reactions. So let's start with bromide. We're going to say that our nucleophile is bromide, and our base reference reaction is going to be this reaction run in methanol. Now, what's really striking is if you see the difference in this reaction run in methanol, a protic solvent, versus an aprotic solvent like DMF. The reaction rate is hugely higher in DMF in the aprotic solvent, 21,000 times faster. And the same holds true for if we just react this with another iodide, because iodide is a stronger nucleophile than bromide. Its reaction rate happens to be faster in both solvents. But again, putting this reaction in an aprotic solvent results in a ginormous increase from 43 to 65,000 or 6,500 times faster than the baseline reaction. And if we use fluoride instead, what is really crazy is that running this in a protic solvent actually results in a decrease in reaction rate of 6,000 times. But if you run this in an aprotic solvent, what you find is that it is way, way, way faster than any of the other two. It is a much stronger nucleophile in aprotic solvents than bromine and iodine. So my question to you is, why might that be? And we'll talk about why specifically with the example of sodium fluoride here, because you have to have some way to deliver fluoride anion, and to do that, you can use sodium or potassium or even hydrogen, but this time we're going to talk about sodium. So if you dissolve sodium fluoride in water, let's say, you have two types of interactions. You have cationic stabilization by lone pairs in the oxygen that are very happy to make some types of ionic interactions because they have partial negative character from this OH bond and are basically drawn to this fully positive Na ion. The fluorine negatively charged anion, however, has a lot different story because it is a very strong hydrogen bonder. In fact, it's going to take a hydrogen bond for just about every lone pair it can. And so the fluorides are going to be very unavailable to do the reaction because they're going to be, the fluoride ion is going to be tied up in all of this hydrogen bonding. So because of that reason, the reaction is going to go very slow in solvents that can donate a hydrogen bond to the fluorine. However, in an aprotic solvent, the story changes because now, again, you have the cation stabilization, but you don't have any anion stabilization because there are no good hydrogen bond donors, no acidic hydrogens that you can really do some good hydrogen bonding with. So because of that, you are essentially raising the energy of the reactants in an aprotic solvent because you don't have any energy of stabilization with this fluoride anion, and due to that, the activation energy you observe here for aprotic versus here for protic is much lower. The protic activation energy, the protic solvent activation energy is much higher. This is the activation energy, and it is much larger than you would say for the one without anion stabilization. So for this reason, the energy of activation is lower and the reaction goes much, much, much faster because the energy of the reactants was increased simply by removing the stabilization. And the same effect happens with stronger hydrogen bond donors as well. So typically SN2 reactions are run in aprotic solvents. That way you don't have to worry about the hydrogen bonds lowering the strength of the nucleophiles that you want to make the reaction happen. So that is section 7.3. I hope you enjoyed it.